Hello, everyone, and welcome to this final video of lecture 3. We have already talked about uh, both symmetric key encryption algorithms and asymmetric key encryption algorithms. In the last video, I've talked about two well-known asymmetric key encryption algorithms, including RSA and Diffie-Hellman algorithms. And now today I'm going to talk about some applications of uh, asymmetric encryption algorithms. Okay, the first application that we will be talking about is digital signatures. Okay, per definition of National Institute of Standard and Technology, a digital signature is defined as this: the result of a cryptographic transformation of data that, when properly implemented, provide mechanism for verifying the origin of uh, some message or some data, and also help us verify the integrity of data, and also helps us verify the uh, non-repudiation of data. Okay, uh, it means that it works like a human signature. When I sign somewhere, for example, I sign uh, in a part of my check or a contract or whatever, that signature means a couple of things to you. It means that it was, for example, this specific person who has signed here. That's first thing, and it means to you that things should be kind of unchanged. Data shouldn't be tampered. Data should be clean, and the integrity of data should be clean and safe. And another feature is that later the person who has signed it, for example, let's say I am the person who has signed it, I cannot uh, decline, I cannot claim that it wasn't me who signed that letter. In a way, it's a two-directional certificate. First, you trust on me and you realize that it was me, and I cannot decline that. I say I cannot claim that it wasn't me. So that's why we say that purpose of digital signatures are for authentication, user authentication, data integrity, and non-repudiation. It means that the third one means that the person who has signed will not be able to later decline and claim that it wasn't me. No, because that the signature is something which is uniquely generated by the signer person, and the signer cannot later decline and claim that it wasn't me. So digital signature, what are the digital signatures? Name might be somehow confusing, but at the end of the day, they are data-dependent patterns of data, which are being generated using some function. We will be talking about them. For example, today we will be talking about one type of digital signature, which is being generated based on RSA algorithm. So we will be using RSA in order to generate digital signatures. So when we say digital signature, it means that we are generating some patterns of data, some patterns of 0 and 1, some binary data that helps us to kind of attain these three important properties that we just mentioned. Okay, per FIPS 186-4, we have three major digital signature kind of methods or algorithms. One of them is DSA. The other one that we will be talking about is digital signatures using RSA, and digital signatures using elliptic curves algorithms that we will not be talking about. I'm just kind of naming them. Okay, one important factor that we should consider when we're talking about digital signatures is that digital signatures are not designed to address or to attain data confidentiality. Data confidentiality is not supposed to be protected using digital signatures. So it means that if you digitally sign the file, or if you have a digital signature on a piece of information or a message or a file, that piece of information only because of the digital signature cannot be protected against eavesdropping or against sniffing or against anything that somehow relates to confidentiality. And later, when we see the details of example digital signature generation algorithms, you will see that digital signatures work based on a portion of the message, not the whole message. You have a message, you take a part of that, and based on a part of that, you generate the digital signature. So that's why they cannot be used in order to protect the confidentiality of the data. Even if we, here is a third kind of point about digital signatures. Even if we encrypt the whole message using digital signatures, even that one is not going to be helpful, because I'm going to make a kind of strange statement here, because digital signatures are using private keys for encryption, and they will be using public keys for encryption. So this is something that I just made it. So in order to open that kind of point or statement that I made, I need to go to details of one of the digital signature algorithms. We'll be talking about the digital signature algorithm that uses RSA. Okay, we get two parties, Bob and Alice. Bob wants to send something to Alice, and of course, Bob wants to make sure that digitally sign that information or that message so that Alice can trust on the information that comes from Bob. And what Bob is doing is this. Bob takes the message, and after taking the message, passes the message through a hash function. So we get a hash digest or a hash function of the message, and the hash function now is going to be encrypted. But here is a very kind of important thing, which is different than whatever we have said so far. The output of the hash function is going to be encrypted using the Bob's private key. Bob encrypt this using his private key, not his public key. So Bob's encrypt this using his private key, and this is the only portion of the message which is being encrypted. The rest of the message just will be transmitted as is without any change. And then this encrypted version of the hash function is the actual signature that we will be appending that to the message. So Bob sends this portion, the actual message, the original message plus the signature to the Alice, and Alice receives that. So Alice receives this. The signature part is the thing that Alice double check that. How Alice generates, again, generates the same hash function for the message, and the hash function is going to be compared against the hash function, which is the hash portion, which came from the Bob, which is now being decrypted using Bob's public key. So Bob's public key will be applied here to decrypt the S, the portion of the message that we named it S. And that should, after decryption, it should give us H. And then these two H now are going to be compared against each other. If they are equal, if they match, it means that yes, this is right, and the message was signed by Bob, and the message has sent by Bob, and the message has been sent by Bob, and also the message integrity is clean. Why? Because if something, if any of these bits has been changed or tampered by some attacker during the transmission, so you have a 0, for example, here, that attacker made it 1, change it to 1, or 1, you had a 1 here, that attacker changed it to 0. In that case, the hash function will be something else, and the decrypted part of the hash function will be something else, and then they don't match. So this is how digital signature works. But like I said, here I made a kind of strange application of RSA. or asymmetric. And I said that Bob is going to use his private key and Alice is going to use the Bob's public key. Okay, first of all, I'm going to talk about this in multiple from multiple aspects. First, I'm going to say why this works, why we believe that Alice is able to decrypt the message using the Bob's private key. Okay, you remember, I'm talking about here, you remember we, in the previous video, I've talked about the Fermat's little theorem, and I said that once we encrypt something using an asymmetric encryption algorithm, we get the message M, and we calculate M to the power of E, which is the public key, and we call this C. And then later, we again take another exponentiation to the power of D, which is the private key. And later, we showed that based on the, I didn't actually show, I just mentioned, based on the Fermat's little theorem, M to the power of ED, if the of course, we are talking about in modular arithmetic. If everything is modular n, this equals m. So here we are talking about m to the power of e times d. Does it matter if I say m to the power of e times d, or I say m to the power of d times e? No, it doesn't matter, because we are multiplying, and you know that multiplications, you can substitute operand in multiplication. So m to the power of de, I can say m to the power of d to the power of e. And if I see this as ciphertext, this means that we have encrypted the message using using the private key, because D was the private key. So the reason this works, the reason this algorithm works, is that we have this math equality here, and m to the power of ed equals m to the power of de, and we can write it as m to the power of d to the power of e. And if I consider this as a ciphertext, this means that I have encrypted the ciphertext using the private key. And now I can decrypt it using the public key. So this is a feature that we have it for asymmetric encryption algorithms. If you use the one key for encryption, you will have to use the other key for decryption. But of course, one of them we keep it secret, and the other one we make it public. And we are just naming them public and private, and it doesn't matter. Each one can be private or public, but the private should be kept only for the sender, or for the initiator, the one who generates data or wants to encrypt the data. And of course, this is the second point I'm going to make, the second argument. Of course, in the message authentication, in the digital signatures, we don't want to reveal the Bob's public key, Bob's private key, because if here is the Bob, and Bob is the originator. If Bob if Bob uses his own public key, he will end up having to sharing his private key to Alice. And Alice doesn't have the private key. The private key is supposed to be private. The private key is not supposed to be shared. So because of that, we make this smart move, and we say, okay, how about Bob comes and encrypt the message using his own private key instead of his public key. If okay, so if Bob encrypts the message using his own give me a second. Yeah, if Bob comes and encrypt the message using his own private key, now he can keep his private key private, and he doesn't have to share it with anyone. And the public key of Bob, everybody knows that. Everybody knows that, and it is okay if we assume Alice has access to that, and Alice use it for decrypting the signature part, And based on this theorem, it works. If Bob encrypts with the public private key, Alice will be able to decrypt it using the public key of Bob. And here are the kind of notation that we can actually look at them. Although they are, I have somehow talked about them, but I have them here as a math written so that you can also look at them. And yeah, here we say to sign a message M is supposed to be signed. We first generate the hash of that message and we call it H, where function H is a hash function, and it might be any function. Of course, it should be some unkeyed hash function. We don't want to use keyed hash function to make another kind of to make need for another key. It's not required. And then this is a signature, which is the hash function of our message, of course, to the power of D, which is the private key of Bob, to the power of H to the power of D mod N. And this is going to be the signature. And we send the signature to the second part. And here is the signature verification process, or checking the signature, how the Alice makes sure that the message that came from Bob is really from Bob. Like I said, she takes she takes the signature, and first she generates another hash function from the message, again another H, let's call it H prime. Now is going to be checked using the S to the power of E mod N. S to the power of E mod N, it means that we are decrypting the ciphertext or the S using the public key of the Bob that we called it E. This is the decryption process. And if H prime are equal, it means that yes, that message is really signed by Bob and everything is clean. Okay, now I'm going to talk about or compare digital signatures versus HMAC. We've talked about HMAC, hash message authentication, and I just want to make sure that we are on the same page. This is what we have talked about it when I talked about the hash functions. They may somehow seem similar. That's why I put them next to each other in order to kind of compare them against each other. Here is the digital signature. We take the message M, we take the hash of that, the hash which is here in yellow, the hash digest which is here in yellow is going to be encrypted using the A's private key. Here, Alice and Bob are changed. Alice here is the sender in this slide number 136. And then she uses her private key, encrypt it, and append it to the message and send it to Bob. And Bob takes the message, generate another hash function, decrypt this part using the Alice public key, and compare them against each other. This is a digital signature that we just talked about it. And here is the HMAC, just for refreshing your mind. In HMAC, we have the message. The message is going to be hashed using a keyed hash function. So we have a hash function that works based on a key, and we generate the hash digest. The hash digest, which is here red because it's generated using a keyed hash function, is going to be appended at the end of the message. And here is now the message that we will be sending it. And at the receiver side, we do the same thing. The receiver, which is here Bob, receives the message and looks at the kind of plain text or the message and generate the hash function using the same key, and compare and generate, of course, a hash or a MAC. And these two parts now are going to be compared against each other. If this part, which is generated at the receiver side or the Bob's side, and this part which is being sent from the Alice or sender side, if they match, it means that okay, the message is authentic and the message authentication kind of approves. Otherwise, it means that something is wrong. Either message was tampered or the message is not authentic. It comes from a different sender. But here you see that in terms of difference with the digital signature, here we are talking in HMAC, we are talking about a key which is pre-shared. We have a pre-shared key between the sender and receiver. And basically what we are, here there is no encryption at all. We have only a hash function, and a secret key should be already shared between the sender and receiver. So the difference between the digital signature and HMAC is this. And of course, another big difference is that in digital signature, you have that repudiation property as well. It means that whenever Bob receives something from Alice, Alice cannot decline that, cannot say that it wasn't me who sent that data. But in authentication, that's not the case. That might be, that may happen. Okay, we are done with digital signatures. Now I'm going to talk about the very last application of asymmetric encryption algorithms, which is called digital certificates. Okay, now first open the problem and talk about the situations that we have some problem, even with having something like RSA or one asymmetric encryption algorithm. The problem that asymmetric algorithm still cannot address is the case that, let's say you have Alice and Bob, and they are supposed to communicate. Here is Alice and Bob, and adversary comes, adversary generates a pair of public and private key and shares them with Bob, saying that, okay, I am Alice and this is my public key. If you want to communicate with me, you can use that key. And this way, the adversary can kind of fool the Bob or any party and receive the information which was supposed to be securely only delivered to Alice. Because we are saying that basically what the adversary node is doing is that the adversary node is impersonating the Alice role. He or she is pretending that I'm Alice and generates a set of key, keeps the private for himself, and sends the public for Bob. And there is no way for Bob to make sure that this is the key which is being generated by Alice, or if someone is impersonating to be Alice. Okay, this is the problem we have. And the solution is this, that we can bind the public key using some owner's identification in a trusted way. What this means is that if anyone comes to Bob and says that, okay, I'm someone and this is my public key, please, if you want to later communicate with me securely, use it. This is not how it should be. Bob doesn't accept private keys like this. Private keys should come with some owner's identification information. This is your private key, and who are you? I need to know. And other than that, there should be some certificate in order to make me sure that you are right, you are the person that you are saying. This can happen only through digital certificates. Okay, a digital certificate can be generated using a specific party in the system, in the network. We have Alice, we have Bob, we have maybe multiple adversaries, and we have a specific node in our network that we call it certificate authority. And the certificate authority is the node that everyone knows him. Everyone relies on him. And this certificate authority is the person or is the node in the network that has already shared his public key to the network. So Alice, Bob, and anyone in the network knows the public key of this certificate authority. So once two person, let's say Alice and Bob, they have decided to start a secure communication, and they just want to exchange their public key with each other. So it's not like this that Alice just comes and sends the public key to Bob. No, Alice goes and asks the certificate authority to send his key to Bob. And the package that certificate authority sends to Bob is not only the Alice key, it has multiple things. It has three major things. First, Alice key. This is the public key that Alice was wanted to share with Bob. Okay, that's a part of that package that CA sends to Bob. But other than that, there are also some identifiers from Alice that later will be used by Bob to make sure that this is Alice. And also a signature, a digital signature from CA itself. Because if you don't involve the CA in this process, again, someone may come and impersonate that, okay, I'm CA. And using this digital certificate, we can verify the CA signature, and we can make sure that the key that has been shared with us is really coming from someone authentic. Okay. In some situations, we may want to revoke or cancel some of the certificate before their expiration time. Of course, we can assume for having some expiration time for any certificate, but some certificates are needed to be expired because, for example, Alice and Bob, they just finished their communications and they don't need to send any more data. So they want to terminate the session or terminate the communication, and they want to expire the certificate. So if that happens, having that said, we have a list of kind of certificate that are canceled or revoked. So it is called CRL, Certificate Revocation List, which is actually a blacklist, which is stored somewhere in the CA, and it keeps the serial number of the revoked certificate. Because the CA wants to know that which certificates are just revoked. And of course, CA keeps them, keeps the CRL only until the time that the expiration comes. Once the expiration comes, that kind of revoked certificate will be removed from the list. And the reason is clear. You have a list of certificates which are not, for example, certificate 1, certificate 17, and so on. These are all, for example, 230. These are certificates which are kind of blocked or revoked. They are no longer valid. And of course, here next to these, there are some information: sender, ID of sender, public key, and signature of a CA. These are all here. Of course, if the expiration time comes, you want to delete this from the CRL, from the list of blocked certificate or blacklist of certificate. Why? Because this key might be later used by that sender for communicating with someone else. So that's why we should make sure that once a blacklisted certificate expires, we remove it from the list of certificate who revoked. Okay, now let's talk about a digital certificate, how really a digital certificate works. Here is kind of the way a digital certificate works. These are the information. One, let me write it this way: part 1, part 2, and part 3 of the information. These are the part of information that we include in the digital certificate. The first thing is Bob's information. So here in this example, Bob is trying to send his key to Alice. send his public key, of course. So the first thing is some information, some ID information from Bob. And second is the Bob's public key, because this is basically what they want to exchange. Alice needs to know the Bob's public key in order to be able to communicate with Bob or decrypt the Bob's encrypted package or data. And then the third part of the digital certificate is the CA information or signature from certificate authority. So this information, these two will be provided from the Bob to CA, and CA adds his own signature to that, and then takes the hash of these three parts and encrypt it using the, sorry, this is the CA information. This is not the signature. These are just CA information like ID or something. And the CA takes the hash of these, and the hash will be later encrypted using the CA's private key. CA private key will be used, and then whatever you get is going to be appended to the message, and this message now is going to be sent to Alice. Alice receives this, receives the whole package, and Alice starts double checking. Alice, and these are plain text. These three portions are plain text. Alice again generates the hash function. This is the hash digest. Hash digest now is going to be compared with the hash portion, which is being decrypted using CA's public key. I told that everybody has the CA's public key. CA is someone that everybody trusts on. So everybody has the public key of CA, and everybody trusts on CA. So everybody can trust on the public key of CA as well. Alice will be using the CA's public key, decrypt the hashed portion, and compare it against the hash that she generated herself. If these two match, it means that, okay, signature is okay. This is really Bob's public key. Nothing has changed, and everything will be okay. So in that case, Alice can trust on that public key and use that public key for future secure communication with Bob. And of course, the same thing may happen between Alice and Bob. If Alice wants to share her public key to Bob, Alice sends these two portions. Let me clear. Yeah, Alice generates these two portions. This is gonna be Alice ID plus Alice public key, sends them to CA. CA add his own information and then generate the hash, encrypt them using CA's private key, and send everything, sends the whole package to Bob. Bob receives this, generates out of these three, generate another hash, and decrypt the hash portion which is received from the CA and compares them against each other. If they're matching, it means that everything is okay, and Bob now can trust on the Alice public key and will be using it for decrypting information. Okay, one situation that we need to consider also is the case at which we have multiple CAs. If we have a big network, of course, the CA will be recalled by many initiators that they just want to share their public key. For example, let's assume that we are talking about ANT and we have minimum 10,000 or 1,000 active users. They want to send secure information. And we have only one CA certificate authority. Everybody connects to the CA and sends his or her public key plus ID to the CA, and CA is supposed to prepare a package and send it to the person who was asked by the requester. So in that case, the CA becomes a performance bottleneck. It means that everybody needs to, for starting a secure communication, everybody needs to communicate with the CA, and CA will be very busy, it might not be from the performance point of view, it might not be the ideal situation. So in that case, if we have a big network, people say one approach might be this, having multiple CAs, CA1, CA2, and up to CAN. And every CA takes care of a portion of the users. For example, you have 10,000, 1,000 of them goes to CA1, second 1,000 goes to CA2, and so on. And out of them, for example, let's say 100 or 50 are active users. So the number of active users per every CA will be reduced. We have situations like this, that we have, for example, I and J, they want to share keys. One of them wants to send his public key to the other one, and they are not under the same CA. I is working under CA1 and J is working under CA2. What should we do? How can we have them exchanging their key? The approach that can be used is called hierarchical certificate. In a hierarchical certificate, we have a couple of nodes under the umbrella of every or each of the CAs. And we have, at the higher level, we have a root CA that somehow coordinate and works between the CAs. So if the two nodes like I and J, if they are not under the same CA, each one communicates with his own local CA, and the CAs now communicate with each other through the root CA. And that this way, they can in the kind of key exchange between the nodes which are under two different CAs will be possible, will be doable. Okay, for today's attendance code, please use this word certificate with uppercase C. Certificate with uppercase C, please use it for attendance code. And now we are ready to talk about the very last technique for this lecture, which is called digital envelope. In some situation, we want to protect the message without needing to exchange any key. For example, we want to send some secure information to someone, and that's the first and the only communication that these two nodes are going to have. So arranging for key exchange and stuff like that, it might be time consuming, and it might not be kind of favorite. So what we do is that we generate a message, and the message, and also we generate a random symmetric key. Look here, this key, this is a key, but it's generated randomly. It might be anything. And then the message is going to be encrypted using this random key. So whatever, using, for example, DES or AES, whatever. And then key itself is going to be encrypted using a public key. We are talking about, for example, Alice and Bob, and let's say here is Alice and here is Bob. And Bob knows the Bob knows the Alice knows the Bob's public key. So encrypt the key itself using the Bob's public key and append it to the message and send them to the Bob. And now Bob receives. Bob performs something like this. First, it kind of extract the message, but it needs a key for that message. The key is a part of the message, but the key is encrypted. So Bobby uses his own private key in order to decrypt and get the actual key. And once Bob gets to the actual key, now he can decrypt the message and get the message to the plain text. And this way, they communicate without needing to share the key. Like I said, this is for situations that we don't want to share key between Alice and Bob. When I say we don't want to share key, I mean we don't want to share symmetric key, because here we are using private key of Alice, public key of Alice, and here private key of Alice. Sorry, Bob. In our example is Bob. Bob is the receiver. Public key of Bob and private key of Bob. So there should be public and private key between them shared, but the symmetric key is, we don't need to share that. We don't need to share. We instead of sharing the key, we just basically what we do here is that we are sharing the key and sending the message in one single step. The message is encrypted and the key is also there, and all of them are done in one single step. If you don't want to do a digital envelope, we should be doing it this way. We do first we do something like RSA, we exchange their key, and then we exchange the key of DES. The DES key is going to be exchanged, and then the message is going to be sent using encrypted by DES. But this way, we only have the key exchange for RSA, and then second step, the message and the key are going to be sent at the same time. So we somehow save a little bit of time. And of course, this is good if there is only one-time communication between Alice and Bob, if they don't want to communicate too much. Okay, this is the final topic that we have for this lecture. Before kind of finishing this recording, I'm going to also talk about the exam and preparation for the exam. Give me a second. I'm going to share my screen with you. Okay. Let me share again, because I'm not sure if it has been shared. So you will receive a copy of this message over Blackboard. At the time that I'm talking, I'm recording this video, the Blackboard is done and I cannot communicate with you, but you will be receiving a copy of this message. This is a plan that we will have for the second exam. Our second exam is planned for somewhere in the week of, in the second week after break. So I'll be making the exam available for you between March 21st and until March 25th. So you will have starting from 8th March 8 morning, 8 a.m. March 21st until 8 p.m. March 25th, which is something about 40 hours. So you have time, and it's similar to the previous exam. You started and you need to finish it in one session, and that session is going to be 90 minutes. Everything on Blackboard. So this is about the exam itself, and you need to, of course, study lecture 3, which is basically everything about encryption and hash. All we have had 6 recordings and 8 recordings, and you need to watch all of them, look at the slides, and if you need, you can of course refer to the textbook for more details. Okay, this is the exam itself, but we have, similar to the previous exam that we had, we also have a sample question which is going to be out by 21st. And what I will be doing is I upload them on Blackboard as an extra bonus assignment. Again, you would have the chance to answer them on Blackboard, and if you answer them, you'll get extra bonus. If they are not mandatory, you can kind of opt out and don't answer them. That's okay. And then we have a Zoom meeting, which is I planned it for 22nd, March 22nd, 9 to 10 a.m. I know that this time may not work for all of you, but trust me, it is not easy to find time that works for everybody. What I will be doing is I record the video and put it on Blackboard. So if you have a question that you want to be answered, you can email me the question and I'll be answering your questions in the recording session. Or you can ask one of your friends if he or she can attend, and they can ask on behalf of you. And of course, all questions will be answered and will be recorded. If you don't have time to attend, you can watch the video. And basically, this time you are mandated to watch the video. So for the week of exam, which is the week March 21st to March 25th, and we don't have any recording. There is no video recording. Instead, we have only one video that you're mandated to watch it and find the attendance code, and that's the recording of the Zoom session or Zoom meeting. So I record the Zoom meeting, I upload it on Blackboard. There would be attendance code for this. You need to find it, and you need to, like normal video lectures, you need to upload it on Blackboard in order to get the attendance for that. Other than this, there is no video lecture. I'm not going to open anything new. That's the only thing that I want you to have enough time in the week, in the exam week, in order to use your time for getting ready, getting prepared. And for the exam itself, please make sure that you have previous to exam, ahead of the exam, please make sure that you have studied the lectures, you are ready for the questions. And of course, slides and books are open, but I designed the questions assuming that you have already studied them and you have already have some level of mastery on them. So I don't want you to go and search for the answers. That's why if you see that the time of exam is not kind of long enough, that's why I am assuming that you have already get prepared for the slide. And for someone who has prepared previously, prior to the exam time, the amount of time that I'm giving for the exam should be enough, even more than enough. I would say 60 minutes or something even less than 60 minutes is enough, but I'll give you 90 minutes. But of course, that's for someone who has prepared. If you are not prepared, of course, 90 minutes is not going to be enough for you, and you will lose some part of the scores. Okay, that's it for today. Thank you all for attending this class, and I wish all of you the best for the exam and for this last week. Like always, you can email me anytime if you have any question, and I'll be happy to answer. Take care and have a good rest of the day.